Today, the first talk will be by Netta Engelhardt, who will be telling us about complexity of training.
Okay, thank you very much. Thank you for organizing this workshop. The symposium was already wonderful, and we're looking forward to the next couple of days and various experiments. Okay, so this talk is based on several papers, recent, one of which hasn't even come out yet. A couple of papers with Jeff and Arvin from last year, a paper with Chris, Daniel, Jeff, and Sharia from this past summer, and one paper with my student Lisa Yang, which will hopefully appear next week. And so the topic is complexity coarse graining, and I'll explain what I mean by that, in particular in the context of the black hole information problem. So, as usual, we're having issues. Okay. All right. So why talk about complexity coarse graining in the context of gravity? So I would say that computational complexity has emerged, pun intended, as an important ingredient in the emergence of space-time over the past few years, past decade, a bit longer than that. And in general, for space-time emergence, and in particular in the context of black hole thermodynamics and the emergence of the black hole interior and the black hole information paradox. Now, I'll give a couple of examples of the way in which complexity comes in with gravity. Just a couple of examples. There are many others. For example, if knowing or not knowing if the Hawking radiation is being decodable, in other words, being able to decode the Hawking radiation is something that requires exponential complexity. So whether you know or not that the Hawking radiation is being purified, that depends on whether you have access to exponentially complex data or whether you have an exponentially complex algorithm. Another example of an instance where complexity comes into gravity and black hole information and black hole thermodynamics is this idea of an entropy, which is coarse-grained, a coarse-grained entropy, the so-called simple entropy, which coarse-grains over essentially high complexity. And in fact, it's possible to show in holography that this particular coarse-grained entropy computes the Bekenstein-Hawking entropy of a black hole formed from a pure state. So this gives us another handle on black hole thermodynamics where the coarse graining is over high complexity. Now, in this talk in particular, I'm going to focus on the relevance of complexity and complexity coarse graining in understanding Hawking's analysis, the non-unitary analysis of an evaporating black hole. It does work. Okay. So what question am I interested in? Well, here I've drawn for concreteness the picture of an ADS black hole evaporating into a reservoir. In general, some parts of this talk will be specific to ADS CFT, and some parts of this talk are going to be aspirationally more general. But in this case, here we have an ADS black hole. It's evaporating into a reservoir. We have two different ways of thinking about it. We have this semi-classical effective field theory description, and then we have the dual sort of fundamental description, which takes into account the quantum degrees of freedom, which is lower dimensional in ADS CFT. This is the CFT and the reservoir. Now, one intuition that we often have when it comes to effective field theory is that we want to think of a calculation like Hawking's calculation as a consequence of coarse graining. That we have an increasing entropy, an entropy which is larger than what the fine-grained entropy should be. And so it stands to reason that there's some kind of coarse graining involved. And so the question that I want to be asking in this talk is, what is it in the language of the fundamental description, this dual CFT and ADS CFT, what is it that Hawking actually computed? So in other words, where was Hawking's mistake, again, in the language of the dual CFT and the language of the fundamental description of the black hole? So in an evaporating ADS black hole, so again, to be concrete, coupled to a bath, we have two possible ways of computing the Hawking radiation. I should say at least two possible ways of computing the entropy of Hawking radiation. One of them, the more recent one, is the quantum extremal surface formula, which gives us the page curve, unitarily evolving entropy. And the second one, of course, is just what we call Hawking's calculation, which is the entropy that goes up and then keeps on going up until eventually plateauing. And of course, these two give different answers. That's the whole problem. And in ADS, we can ask where in the language of the dual CFT, the language of the fundamental description, where do these two approaches diverge? So what is the difference between these two approaches? What's missing in Hawking's calculation? What did he coarse grain over? So if you'd asked me before 2019, before we did the page curve calculation, where Hawking went wrong, I probably would have said something along the lines of, Harlow-Hayden argued that the Hawking radiation, decoding the Hawking radiation is exponentially hard. So maybe, somewhere, somehow, Hawking's calculation is computationally limited. And what this is referring to is the fact that if you throw a diary into an old black hole, you wait a little bit, Hayden Preskill tells us eventually the information is accessible in the radiation, but Harlow-Hayden tells us that actually accessing it, actually decoding the radiation so that you can read the contents of the diary, that's going to be exponentially hard in log dim h, where h here is the whole. So this is the basic logic behind why we might imagine that Hawking's mistake comes as a consequence of just not being able to see that the radiation is being purified, not being able to decode the radiation on account of not having access to this kind of computational power. So you could say Hawking's calculation is implementing some sort of complexity coarse graining. Again, this is just sort of vague intuition. And now, if you ask most people now, probably the answer would be that he used the non-minimal quantum extremal surface. He used the wrong quantum extremal surface in some sense. This is some sort of a subleading saddle. Yeah, Rafael. So when I say Hawking's calculation, I mean the rough non-unitary analysis that gives you an entropy that goes up and keeps going up and then plateaus. And how can you reproduce that calculation? So you could imagine reproducing it potentially by using the wrong quantum extremal surface or a so-called disconnected saddle in the gravitational path integral. Sure. So if you prefer, when I say Hawking's calculation, you can say non-unitary analysis of black hole evaporation. So this is a way of asking if we were to try to do an ADS CFT calculation that would reproduce an entropy that was going up and then eventually plateauing that behaved non-unitarily, how could we possibly do it? And one way of imagining that you might do it is by using a quantum extremal surface, which is non-minimal. So that's right, exactly. If you compute the entropy directly, yeah. Yeah, so well, I mean, or we could, right, so we could ask the question, and I will ask the question, how do we compute this directly? But if you have to hold on a little bit for that. Okay, so but this is one perspective that you'll often hear at conferences like this. What is the I won't comment, the non-minimal quantum extremal surface. So we know the correct minimal one computes the page curve, and then the question is maybe the non-minimal one computes what we call the Hawking curve, where the entropy goes up and doesn't sort of turn back around. And so these two perspectives, the question that we might ask is, are these two this one and the same thing? Is complexity coarse graining the same as using kind of a wrong quantum extremal surface? And is it true that in general, there's some kind of implicit coarse graining over complexity in Hawking's calculation? Yeah, Horacio. The same as, sorry? So you're asking what about what's the difference between this and a lump of coal, essentially? Yeah. So right. So the difference between this and a lump of coal essentially is that the lump of coal doesn't have a nice effective description. There's like a nice semi-classical emergent geometry in the lump of coal. So you could do a similar analysis, but it's not really clear why you would want to. Here we have two different descriptions, both of which look pretty good. So it's always log of the dimension of the Hilbert space. So we could talk about that. If you just, I'm going to define what I mean by complexity coarse graining in a minute. This is all just motivation. So if you just hold on, I think it's just going to become clear in a minute. Okay, so the question is, can we model Hawking's analysis of an old black hole using some kind of complexity coarse graining? And I'm now going to define what I mean by that. So this talk is split into three steps. The first step is giving a geometric intuition from ADS CFT of what this complexity coarse graining might look like. We're going to define it. We're going to talk about the holographic realization of it and relate complexity coarse graining to non-minimal quantum extremal surfaces. And then you can't quite see this, but the step 2 is doing this in a quantum code model. So that's where we're talking really about fundamental degrees of freedom. We'll do it in the quantum code model. And we'll talk about how in the quantum code model, complexity coarse graining is also reproducing Hawking's entropy curve, the one that goes up and doesn't turn around. And then finally, I'll talk a little bit about attempting to do complexity coarse graining via some kind of a quantum learning algorithm and see if you do a complexity coarse graining and then ask a learning algorithm what it can learn about the Hawking, about the true evolution of a black hole, and we'll find that it's limited in what it can learn. So let me begin with defining what I mean by complexity coarse graining here. So this can in principle be done for any system, including a lump of coal. It doesn't necessarily have to be gravity. We're going to be particularly interested in it in the context of gravity, because that's where we think it's meaningful to understand from the Hawking perspective. So we're going to consider some system A, some quantum system A and a state psi A, pure or mixed. I'm going to call a density matrix also a state. And we'll define this SA here, which is I'll call it the simple set. This is the set of all states on A that agree with our original state psi A on the expectation values of simple observables. And this is, of course, everything here is approximate. So this agrees up to exponential corrections in log of the dimension of it. So simple here, I mean that these operators are sub-exponential in complexity compared with log A, in log A, log of dimension. So yes, that's right. So now for the coarse graining step, what we're going to do is we're going to define the so-called simple entropy, which is going to be the maximum over it's a maximum von Neumann entropy over all states in the simple set. So this is a coarse graining procedure since we're maximizing the entropy. It's a maximum fine-grained entropy, but we're maximizing over a large set of states. And so you can think of this as the maximum fine-grained entropy that is compatible with a simple observer's measurements. And so we're going to call this simple entropy or the coarse grained entropy. And then the state that actually gives you the maximum is going to be the simple state or the coarse grained state. So this is, again, it's a higher entropy state. So we think of this as a coarse graining procedure. And so this is what I'm going to call complexity coarse graining. This is a procedure, I should say, that Aaron Wall and I wrote down in 2017. It was refined with Jeff and Arvin more recently. All right. So the interpretation of this coarse graining in gravity, what is it? I promised that geometrically in ADS CFT, we have some interpretation of this. And the answer is that you can compute this coarse grained entropy, the simple entropy, using non-minimal quantum extremal surfaces. So the outermost quantum extremal surface in the entanglement wedge, be it minimal or not, is what computes the simple entropy. So the simple entropy of this state is given by the generalized entropy of the outermost quantum extremal surface that's homologous to your region that lives in the entanglement wedge. And in particular, that means that if we have a geometry that looks like this, where we have a non-minimal quantum extremal surface and a minimal quantum extremal surface, here's the causal wedge, and the causal surface. And this is on a moment of time slice. This is the minimal quantum extremal surface, non-minimal quantum extremal surface, causal surface. If we have a geometry like this, then that means that the coarse grained state, essentially its entanglement wedge is everything from X to the right, even though the actual entanglement wedge of the fine-grained state, the actual state, is everything in X min to the right. So we essentially are coarse graining over everything in this region here, the so-called Python sludge. So this is a coarse graining in the sense of bulk reconstruction. We've lost the ability to reconstruct things that are between the non-minimal quantum extremal surface and the quantum extremal surface. And this is going to be non-trivial whenever we have multiple competing quantum extremal surface candidates, such as a situation like this. Okay, so how does this work in the context of black hole evaporation, where we're computing the entropy of Hawking radiation? So we have two systems here that we're using for the calculation, right? We have the fundamental description, which we can divide up into, in the case of the ADS black hole, the CFT, we'll call B, and the radiation, the reservoir, which we'll call R. And in the effective description, the semi-classical bulk, we can talk about different modes, the left-moving modes, the right-moving modes. We're particularly interested in the outgoing modes for computing the entropy of the radiation. And so we have the reservoir, we have the right-going modes, the outgoing modes here. And we're going to approximate these as being in a maximally mixed state between them. So highly entangled state, high little r, capital R. So if psi capital R is the state of the radiation, once we've traced out the CFT here, capital B, then is it true that the simple entropy of psi capital R is equal to the von Neumann entropy of the reduced density matrix chi RR when we trace out over little r? This is what we want to be true if we want the Hawking radiation to be the Hawking entropy to be computed by the simple entropy. So let's take a look at this. Before the page time, we're going to compute the von Neumann entropy of the radiation just using the radiation itself over here. Now, after the page time, we have a new quantum extremal surface that dominates over here. But remember, now we're not looking at the dominant quantum extremal surface, we're looking at the outermost quantum extremal surface. And that doesn't change. And so we are still going to be computing the entropy using this one over here. And what that means is that we're going, instead of getting a page curve that goes up and comes down, we're going to get a curve that just continues to grow until the black hole's finished evaporating. So we find using this, this analysis, using the fact that the simple entropy is dual to the outermost quantum extremal surface, we find that in this ADS CFT picture, the simple entropy of the radiation is computing the Hawking entropy, meaning the entropy that is non-unitarily evolved. Okay, so that gives us this geometric connection between coarse graining over complexity and the non-minimal quantum extremal surface. Both of these appear to be calculating an entropy which is consistent with a non-unitarily evaporating black hole. Now let's talk about what happens when we go to the quantum code model. So in this recent paper in July, we introduced a model for encoding the effective description, the semi-classical bulk, in the fundamental description. And that model is a quantum code model that's had incorporated a number of nice elements, such as the quantum extremal surface formula. Now, I think at this point, I and my collaborators have given an exponential number of talks explaining what the model is. So I'm going to be very brief in the description of the model, since today I'm much more interested in the applications of it. So I'm just going to sort of flash this up here and say a couple of words about it, since there are many talks online and all of you have probably seen at least one talk by one of us on it. So the basic idea is we have this encoding map V that goes from the effective description into the fundamental description. Now, again, this realizes a number of nice properties about ADS CFT, which is what we were looking to do. Here, I've given one example. We have three models for V. This is one of them. We call it the so-called dynamical model because it incorporates the dynamics of an evaporating black hole. So capital B and capital R are systems in the fundamental description. This unitary U0, U1, U2, these are random unitaries. And the idea here, we have some left moving modes, we have some fixed degrees of freedom, we have the radiation here. Now, from the perspective of the fundamental description, this just describes unitary evolution. But if you're going to look at the map that actually encodes the effective description into the fundamental description, then what happens is you start out with these L modes, these psi naughts, these little r, capital R, and you find that you have to do post-selection on in little r. So this is the sort of lightning overview. The main takeaway that I'm going to need here is that because we have a large number of null states in the effective theory, V is going to be a non-isometric encoding. So this is the main takeaway. This and well, just the general code structure is the main takeaway from this setup. I really won't use details of this code very much in this talk. Okay, so what about the simple entropy in this code? So we want to be able to compute the simple entropy, and in fact, we can compute the simple entropy directly in this code model using the following lemma. So this lemma does not have anything to do with gravity. This is just a quantum system. So we have some Hilbert space. There's some system, quantum system A. Again, we have a Hilbert space, HA. It tensor factorizes into a sub-exponential number of factors, HA little I. Each one of these is order 1 size. And we're going to let psi A be a state on HA. And the property that we require of psi is that within its simple set, the set of all states that agree with it on the simple observables, within its simple set, there exists a state which approximately factorizes across these tensor factors. So again, approximately means the corrections are small, exponentially small in log of the dimension of A. And what the lemma says is that if these assumptions are true, then the simple entropy of the state psi A is going to be approximately equal, again, with this potential exponentially small corrections, to the von Neumann entropy of this factorizing state phi A. So I'm going to walk through I guess I haven't probably enough time to walk through the proof. Okay, so the proof of this is an equality that we're trying to show here. So you can just show it by showing the two inequalities, one greater than or equal to, one less than or equal to. Well, we know that phi lives in the simple set. So that automatically tells us that the simple entropy of psi A must be greater than or equal to the von Neumann entropy of phi A, since by definition, everything in the simple set contributes to the simple entropy. And so either phi A maximizes the simple entropy and is literally, there's an equality here, or phi A has a smaller entropy. So this is given by the definition of the simple entropy. And what we need to show is that the reverse inequality is also true. So the rough idea here, and I'm skipping a lot of subtleties in the proof here, but the rough idea is that suppose that there exists some state phi A tilde where the simple entropy is less than or equal to the entropy of phi tilde A. So let's just make this assumption. Now, this statement follows immediately from strong subadditivity, or sorry, from just subadditivity, not strong subadditivity, where we're not assuming that phi tilde A factorizes. So that does mean that we don't necessarily have an equality here. Now, we can model the simple operators as essentially operators that factorize across these tensor factors. And they're going to have approximately the same values for all of these operators, for all of these states over here. So we have an approximate equality, or I guess you could write it as exact, but really it's approximate on these expectation values. And finally, we invoke a number of operator entropy inequalities to relate the entropy of phi on these factors to the von Neumann entropy of phi tilde on these factors. And so the proof is really a series of 4 steps put together. This is the first ingredient. This follows by definition. This follows by subadditivity. This follows by simplicity of the operators. And this one finally, this follows by one of our earlier assumptions, which is that phi A factorizes across the different tensor factors. And so basically we put all of these together and we find that the simple entropy of psi A is less than or equal to the entropy of phi A. And altogether that tells us that since we started out with it being less than or equal to, oh, sorry, this is the wrong sign here. And we find that it's going to be, so it was greater than or equal to, and here we find that this is less than or equal to, which means that there must be. So this is the sort of lightning sketch of the proof for that lemma. The question there, yeah. The structure of, so there are quite a few steps that I'm skipping here. I understand. So the operators that go into the simple entropy are operators that are simple. So we're just requiring that these are sub-exponential in their complexity when you start out with some fundamental set of gates. So we don't make any particular assumption about the gates beyond the assuming the existence of initial ones. But so I want to think about that a little bit more to see if it makes a difference. Let me get back to you on that. I'm not 100%. Yeah, Edward. Yeah, that's right. So actually, I'm going to comment in a moment on the structure of the Hawking radiation as relevant to this particular. How many minutes? Sorry, 10 minutes. Okay. Okay. Oh, actually, okay. Oh, so this is where I was going to comment on it. Okay. So so we're going to take the Hawking. We often approximate the Hawking radiation as having approximate product structure, in the sense that we have these modes that are entangled with one another. And so we expect that but certainly in this dynamical model that I discussed, but we expect potentially a little bit more generally, it might be reasonable to expect something like this property for our model of Hawking radiation. This would certainly not be exact, but in the dynamical model that we have, this is in fact an exact statement. We have factorization, and so the lemma does apply. And then once the lemma applies, then we immediately recover the fact that the simple entropy of our state psi capital R is the von Neumann entropy of chi little r, which again is this maximally mixed state of the radiation. So this quantum code model indeed realizes this expectation that the Hawking entropy is being computed by the simple entropy, by complexity Coarse graining. And again, just a comment that this lemma is potentially a little bit more general in the sense that as soon as you have this approximate structure of this factorization structure, then you're going to be able to use this lemma to argue for a relation between the simple entropy and the Hawking. Okay, so the final bit I want to talk about here is a slightly different approach to this and trying to understand something a little bit more general, which is coming from the quantum learning perspective. So this is work in progress with my student Lisa. So here is a goal question, which I'm not going to answer, but it's sort of an aspirational question. So I want to ask, in general, suppose we have some arbitrary reconstruction algorithm, meaning you're given some input in the fundamental description, and you're being asked to produce some semi-classical calculation. Maybe you're being asked to produce a semi-classical calculation, which gives you the page curve. Maybe you're being asked to reproduce a semi-classical calculation that gives you the Hawking curve. So the question is, does an arbitrary reconstruction algorithm, which is computationally bounded, and by that I mean with polynomial complexity, and has access to simple observables, does that predict non-unitary decohering dynamics for an evaporating black hole? If the answer is yes, for any such algorithm, then we might say, well, that's pretty good evidence that Hawking's calculation, that there's a good model for Hawking's calculation, which is Coarse graining over complexity. So this would be a very nice answer if it must be the case that as soon as the algorithm is computationally bounded and it tries to guess the time evolution of a black hole, it gives you this non-unitary evolution. Now, is this true? Well, maybe, I don't know. This is not what we've shown. We have a sort of an intermediate result that is helping us work towards something potentially like this. So the result is the following. If we have a simple reconstruction algorithm, then we can show that this simple reconstruction algorithm, and I'll define more precisely what I mean by that momentarily, it can't accurately predict the time evolution of a black hole. So what we mean by that is that there's always going to be some distinguishing operator or P of M that can tell you that the output of any simple reconstruction algorithm is inaccurate. So it misses the time evolution. It can't quite reproduce it correctly. Okay. So I'm going to be a little bit more precise now in what we actually do and what assumptions actually go into this. So the first two assumptions is we're going to begin by modeling time evolution in the fundamental description via a pseudo-random unitary. Now, a pseudo-random unitary, what we mean by that here is it's a unitary which is efficient to prepare, but cannot be efficiently distinguished from a Haar-random unitary. Now, why is that a good model? Well, we often use Haar-random unitaries to talk about the dynamics of black holes. but how random unitaries are not efficient to prepare, and we expect that the dynamics are actually efficient to prepare. We also sometimes talk about K-designs for the evolution of a black hole. Here we're going to talk about a pseudo-random unitary rather than a K-design. I'm not sure how to prove these results for a K-design. And then we're going to model the black hole state as a pseudo-random state. I think I still have a couple. Okay. So we're going to model the black hole state as a pseudo-random state. Again, it's efficient to prepare, but it's not efficiently distinguishable from a Hall-random state. So, and I should mention there's a connection between pseudo-random dynamics and chaos. And of course, we expect black holes to be chaotic. So all of this is physically motivated. Yeah. Oh, sorry. Okay. So, what's this algorithm, this reconstruction algorithm that I'm referring to? Well, our reconstruction is going to be modeled by what we're going to call the learning algorithm, which has the following properties. So it's computationally bounded, as I already said. It's the algorithm complexity, both the computational complexity and communication complexity, is limited to be polynomial and logged in age. Now, it also has oracle access to simple observables and simple states. And what we mean by that is that the algorithm has access to expectation values of simple operators in simple states. So this is what we think of as being given information about the fundamental description. Right? It has access to some of that information. And its task is to learn U, to output the pseudo-random unitary U acting under pseudo-random state psi. This is what it aims to do. So this is the task of the algorithm. Now, the algorithm is pretty general. It has the following steps. It's first, it's going to learn and query. So it takes a state that it can prepare, and it queries the unitary U with that state, with observables. This is how it obtains the information about the fundamental description that it can have access to. When we're doing something like HKLL, we say, okay, it says that we have access to expectation values of operators. This is a formal way of saying this is how it obtains access to that. Then it uses its polynomially complex circuits to process the input in order to best approximate U. And then it's being cut off to oracle access. It can't ask any more questions, and it's being asked to produce the time evolution of the state psi. And then it applies its best guess at the operator U to guess the state psi. So this is the protocol. Now, how do we define success or failure here? So the algorithm is successful if it outputs an operator O, where on average, so we're averaging over the distribution here, on average, this is approximately 1. And when we say approximately, again, we mean up to exponentially suppressed fraction. And it's going to fail if on average, this quantity is less than 1 minus 1 over poly. So that means it's successful if it's 1 minus 1 over x, and it fails if it's less than 1 minus 1 over poly. Now, after conversations with Scott yesterday, I've concluded that this is not a tight bound. Nevertheless, it actually gives us enough to have a nice conclusion here. So, you could say this is a pretty weak bound, and you can actually learn kind of a lot with producing something like this. But one thing which is very nice that it does for us is it guarantees that there are operators, or more generally PODMs, that can easily distinguish between U acting on psi, the actual time evolution of the actual state, and the output of the algorithm. And so there's going to be some distinguishing states, and we can think of those as kind of operators that live in that Python's lunch that are going to be different in the two different states. So this is how we define success versus failure. And the theorem is if U is a pseudo-random unitary, psi is a pseudo-random state, then a computationally bounded learning algorithm with oracle access, this algorithm that I just described, fails to learn U. And when I say fails, I mean in the context of that equation, how we define failure. And very nicely, this result can actually be generalized to a situation where the algorithm isn't just outputting an operator, but is actually outputting a potentially decoherent channel. So there is hope here that we can make a connection with something that looks like Hawkings. Now, I think I could go through the proof, but I think I have probably only like 2 minutes left. I have 1 minute left. Okay, so I'm just going to go ahead and go through the conclusions. Okay, so upshot. So we have this learning algorithm, which sort of mimics, we want to think of it as mimicking a reconstruction protocol that only has access to simple observables. This is a very general reconstruction protocol. And in this very general setting, we find that even though we give this algorithm Oracle access, so it has things that information it can get for free, don't cost it any complexity, when it outputs its best guess for you, there's still going to be some operators that can easily distinguish between the actual time evolution of the state and the algorithm's predicted time evolution of the state. And our bound is going to still be valid if, I promise I'm almost done. Our bound is still valid if the algorithm outputs a quantum channel instead of an operator. Of course, the million-dollar question here, the thing that we really would like to answer is what are the necessary and sufficient conditions for the algorithm to actually be outputting something that really looks like the, this non-unitary evolution. In other words, for it to output something like a decoherent channel. So I'm just going to leave up the summary over here and I'll take questions. Thank you.
When you make a list of simple operators, if I have simple operator O1 and O2, do you consider a sum of them a simple operator as well?
So anything that you can prepare with a sub-exponential number of gates. So just you're asking if the set of all simple operators forms an algebra, the answer is no.
Subspace.
A subspace. I want to say the answer is yes, but there's something in my head that's telling me that the answer is actually no.
I think
The answer is no. Okay.
I think if you take it to be a subspace, your lemma is going to be very hard to satisfy. There won't exist states with that problem.
That's right. Yeah. So I think it does not. Yeah. I think it does not. The sky chain saying no, so it must be true. It's not a
symbol of subs.
But so you want a discrete set of simple operators? Is that what you want?
You want a discrete set of simple operators. We always work with the discrete case here, but the question is, what do we want to be able to generalize that? And what happens when we do? That's a good question. In the discrete case, certainly things are fine, but
yeah. In a heuristic setup, it's probably like this kind of cross-training happens dynamically only through kind of string dynamics, redshifted string dynamics. In other words, dynamics on the stretch horizon. The question is, what kind of aspect of stretch horizon dynamics leads to this kind of coarse graining, which you can't keep track of the fine structure using quantum computing? Is it fair to say that that's like non-locality, like all-to-all interaction, because your simple operators are selected from the local quantum theory point of view? If you have all-to-all interactions, even though k-local, and that will cause some complexity which you can't decode in polynomial time, and that's what's happening on the stretch horizon, right? So do you think it's fair to man that? Like sorry.
So the simple operators, as you say, are defined in the fundamental description rather than defined in the.
No, in a book. I was talking everything in a book. In a bulk point of view, this dynamics is string dynamics. Of course, it's CFT in the field theory, but it's string dynamics in the bulk because things are absorbed into the stretch horizon and then it's scrambling. And scrambling is completely complex. So that's the origin of this complexity, which you can't decode in a polynomial time using quantum theory operator, right? But what aspect is the most crucial thing? Is that non-locality?
Well, okay, there's non-locality in the sense that the ABS-CFT dictionary is non-local, but beyond that, there's no non-locality involved in this. And there's a difference between the sub-exponential complexity in the effective description and sub-exponential complexity in the fundamental description. And we're only ever talking about in this talk, I'm only ever talking about sub-exponential complexity in the fundamental description.
Yeah, I know. Yeah.
So at least in 1+1 dimensions, we have examples where we understand that the gravitational path integral computes an ensemble average.
Mm-hmm.
And in that situation, it's not surprising that the entropy of the average state can be large, but the average entropy can follow the page curve.
Yes.
And I'm trying to understand how this relates. Would this be inapplicable in those settings? Or is there a kind of map between not looking carefully at using simple operators and averaging over ensemble? In particular, can we?
Well, so you'll notice there was no ensemble averaging in this talk whatsoever, and we don't need it in order. So yeah, we don't need it. Now you could say in 2 dimensions, 1+1 dimensions is very natural, and in that case you could ask, what does this averaging correspond to? I want to say that something like what you said is true. You're not looking super carefully at the simple operator. There's a bit of smearing of averaging. You know, we do talk about averages here in order to get our results, but they're average in the sense we're looking at a typical instance rather than, you know, considering this to be a genuine ensemble. But I think if you want to consider it a genuine ensemble, you can sort of take the same results and interpret them differently.
Netta, could you go back to the proof of your lemma, the slide in part 2? There was this state phi tilde that appeared there, and it seemed like the only assumption you put on that state was that it had entropy greater than the state psi.
That's right.
But then there's this seemingly very powerful claim that all of its local expectation values are very close to the state phi.
Yeah.
Is that really true for any state? Does it have to be within this typical ensemble or this set of simple operators?
Yeah, so because the simple operators we are factorizing across this Hilbert space,
Right.
then for sufficiently small factors, you take the factor to be sufficiently small, then you expect this is approximately true for just about any state typically.
Well, but I mean, say the Hilbert space is of size 2, right? I can certainly construct
Yeah, there's some assumptions that go into the size of the Hilbert space here, yes.
Well, I just mean on a,
The factors are order 1 compared with what we're talking about. So they have to be small compared to the size of the Hilbert space. So there is that assumption. If you have a Hilbert space of size 2, I don't know how to make this work.
but then is there some assumption about the distance between phi and phi tilde as measured on the whole Hilbert space that would cause their distances to be very small in any factor?
No, I don't believe we make any assumption like that. In this, so this thing here, this equation here, essentially only relies on the factorization and having the sufficiently small factors and having these be simple operators. So that's the essential assumption.
This is essentially the same as Horacio's question at the beginning, but in your last model that you presented, can I think of that as the same problem if I want to reconstruct the information from just burning a diary or, I don't know, predicting the weather or something even? What's special about quantum gravity in this setting, or is it just much more general statement about quantum mechanics?
Sure, so it's not that you can't talk about complexity coarse graining in an arbitrary quantum system, and we certainly define it for an arbitrary quantum system. The difference is that there's no real, we don't have two nice descriptions of the emergent description and the fundamental description for something like a lump of coal. We don't have a nice interior, a nice effective interior for a lump of coal, as far as I know. And so I don't know why we would be interested in asking this question in the first place.
Not complex, right? Because you can keep track of everything in quantum theory. That was my question. Stretch horizon is different. It's non-local in the horizon direction. Otherwise, you can keep track of the quantum theory. So everything you can keep track, find structures.
So I'm not seeing the connection, honestly, but maybe we should talk about it offline. Yeah.
Maybe the question is, what aspect of the dynamics of black holes prevents, makes this coarse graining so limited?
You mean the fact that this dynamics are pseudo-random? I mean, that's the main assumption that goes into this, right? That the dynamics are chaotic and pseudo-random.
Another question? Netta again.